Okay, so those of you that are just joining us on the video, we just ran through A, B, and C, and it's all previous knowledge, so you should be able to come up with this. We wrote the volume of a sphere, and then we took the derivative of volume with respect to radius and got this. Then we took the derivative of volume with respect to time and got this. Paying close attention to the chain rule. That's a quick summary for y'all. Now, we're going to do something with this. So part D says, if the radius is increasing at a constant rate of 0.03 inches per minute, how fast is the volume of the balloon changing at the time when its radius is 5 inches? Whoa, that's some information. So now the key to this problem is translating all that information into calculus language, right? So when you see if the radius is increasing, you should immediately think of positive, good. What else? We're in a calculus class. You should think of a derivative, shouldn't you? Because it's talking about change, right? It says the radius is increasing. The radius is increasing. The radius is changing. So that is what? The rate of change of the radius. So this is talking about the derivative of radius, isn't it? With respect to what? Time. So this right here is dr dt, isn't it? 0.03 inches per minute. Now, if you're not sure which derivative is, you can look at the units to help you, can't you? Because the units give away what we're comparing, right? So since it's inches per minute, that means we're comparing some kind of a length to some kind of a time, right? So if you weren't sure it's the derivative of the radius with respect to something, what is it with respect to? Oh, it must be with respect to time, because there's a minute there at the bottom, right? Okay? So now let's read on. The next question, or the next part says how fast, so that's a question. So I'm about to ask a question, so I'll put a big question mark here. How fast is what? The volume of the balloon. There's that magic word, changing. What does that make me think of? Derivative. Of what? Volume. With respect to what? Ah. So that's dv dt, isn't it? That bug that ran into me is dying over there. Got a hard head, I guess. Okay, let's keep on. And it says, now when. This is a really important word in these problems. You see that word there, when? Why is that important? Is the radius always 5 inches? No. The radius is changing, right? So the radius isn't always 5 inches. So they're saying, here we got this balloon. You got this balloon that's deflating, so it's getting smaller and smaller and smaller, and there's all kinds of stuff going on, and that little formula up there kind of governs what's going on, right? And what we're saying is, I'm really interested once the radius gets down to 5 inches. Right? You with me? Oh, it's inflated. My bad. Okay. I'm really interested when that balloon gets big enough so that its radius is 5 inches. So, now, this is really important to understand. Right now, if we scroll back up to here, that first volume in A, or that first equation in A, that's a static equation. You understand what I mean by that? There's nothing happening there. It's not changing. It's just volume equals that, right? I plug in a radius, it gives me out a volume. Everything's set. There's no movement, right? When you come down to C, that's changing, isn't it? It's got change happening all over the place. You got dv dt, you got dr dt. So this is representing that balloon inflating, right? That's the beauty of calculus. It's the math of change. It's not the math of static stuff, right? And things are changing all the time. So that equation takes into account change, right? So here's the key. I can't plug in 5 at that top equation because that would set everything at 5, right? I have to take the derivative first, but once I take the derivative, now it's accounting for change, so I can plug the 5 in anytime I want to after I've taken the derivative. You with me? This is really important. This is the mistake that people make. They plug in all the information at the beginning and then take the derivative, and they get a derivative of 0. And they go, that was an easy one. Right? Because if you plug in 5 there, the whole thing, when you take the derivative, it just becomes 0, doesn't it? Right? So the key is, you got to wait to plug in 5 at the right time. And this is the way I force myself to rate. This is something that I came up with. This is unique to me. You won't find this anywhere else, okay? I created this idea of the ice box. Because I got this stuff going on. It's changing. The balloon's inflating. Everything's getting bigger. The radius is getting bigger. The volume's getting bigger. The surface area is getting bigger. Everything's changing. And I want to freeze time. You get the icebox thing? Freeze time. I think that's cute. Okay? You freeze time. When do I want to freeze time? I want to freeze time when the radius is 5. Right? That's when I want to freeze. Because it's changing. Right when the radius gets 5, I'm going to stop. Stop everything. Okay, now I want to look at this picture. Just this picture right here. Not all the other times. I want to look at just when the radius is 5. So when I'm reading a problem, knowing that that's what's going to happen, when I get information that's only true once time is frozen, I put it in the icebox. If I have something that's true all the time, I put it on the outside. You see what I'm doing here? So for example, this dRdt, is that always true or only true when the radius is 5? It's always true. It's apparently that I'm blowing at a constant rate, so the radius is increasing at a constant rate. Right? It's not getting faster or slower as I go. It's 0.03 all the time. Okay? However, is the radius always 5? No. So inside the box I put a r equals 5. Because that's only true when I've frozen time. It's not true all the time. Okay? How about my question? dv dt. Should that go in the icebox or outside of the icebox? Right. The question I'm asking, what is the rate of change of volume? All the time? No, I'm asking for it, when is it at this specific time, right? So my question actually goes in the box too, doesn't it? I want to know what dv dt is when r is 5, right? Not just any time, but when r is 5. That's the question, right? Okay. Now, have we accounted for all the information in the question? Yes. So now we just got to answer the question. So this is where the related rate idea comes in, right? So I know one rate, right? I know the dRdt. I don't know dv dt. So I'm going to use this equation that relates the two rates to find dv dt. Okay? So I'm going to take dv dt equals 4 pi r squared times dRdt. And that's my equation, right? Now, as I said before, the key to the icebox is I do not plug anything from the icebox until after I've taken the derivative, right? So we had already taken the derivative up there, but if we hadn't done that, what we would have done here is we would have came up with a formula for volume, wrote it out, took the derivative, right? Once I take the derivative, now I can reach into the icebox and plug things in. Because once I take the derivative, now I have a formula that's accounting for change. With me? Before I take the derivative, it's a static equation. It can't deal with change. It has no way to handle change. So I can't plug stuff in that's only true at a certain time until after I've taken the derivative. Okay, that's the key to these problems. Right? But now I've taken the derivative. It's sitting right there. Now I'm going to plug in everything that I know. Notice I'm not setting this equal to 0. That's what I do for optimization problems, right? I'm just plugging in what I know. So do I know what dv dt is? No, that's what I'm trying to find. So I'll leave that as dv dt. Do I know what 4 is? Yeah, that's 4. Do I know what pi is? Yeah, that's pi. Do I know what r is? Yeah, I can plug that in now because I've taken the derivative. So that'd be 5 squared. Do I know what dr dt is? Yes. That's 0.03. Now, just to be cool, we'll probably put the inches in here. Putting the units in can really be helpful. Okay? Now we're just going to simplify this. dv dt is equal to, let's see, 25 times 4 is 100 pi times 0.03. Whoops, sorry. That would be 3 pi. And that would be inches cubed per minute. It's important to include the units because that way you can check to see if you've done everything right. Because what would I expect the units for this to be? The change in volume with respect to time. What should they be? Something cubic per time, right? So do those units work? My volume is changing at 3 pi cubic inches per minute. That's a good volume unit, isn't it? So that reassures me a little bit that I've done something right. Okay? Is this a kick in the pants or what? That's a good thing, by the way, in case you don't understand that vernacular. So again, the key here is, in optimization questions, what are we trying to do? Right, but what do we have to do that? We need to write an equation, right? We write an equation for what? What am I trying to write an equation for in optimization questions? The thing that I'm trying to maximize or minimize, right? You guys' biggest problem is you just kind of remember things halfway. What do I write the equation for? Like a maximum or something like that? Yeah, I think something like that. No, I'm trying to write an equation for the thing that I'm trying to maximize. You want to get that in your head. That's the key to these things is writing an equation, right? You can't just write any equation. You got to write an equation for the thing you're trying to maximize. So if I'm trying that garden problem, if I would have wrote a area formula and derived it, would have done anything for me? Nothing. Wouldn't help me at all. Because what I was trying to maximize, or what I was trying to minimize was cost, right? So I've got to write a cost equation, take the derivative of that, set it equal to 0 and solve it, right? Okay, so that's the key in optimization problems. You write an equation for the thing you're trying to optimize, right? What's the key in these problems? Related rate problems. You need to write an equation, any equation will do, that relates the rate that I know with the rate that I don't know. You with me on that? Would a surface area equation work here? No, because it doesn't involve volume, right? And I need to relate the derivative of volume with the derivative of radius, right? So I need to write in a formula that has both volume and radius in it. So then when I take the derivative, I have the rate of change of r and the rate of change of v in that equation. So they're related, right? Okay. Let's go to the next page. This is so fun. What is the surface area formula for a closed cylinder? I don't know. Oh, actually I do. Okay. Closed cylinder, that's one of these guys. Closed just means it has a top and bottom. So that would be 2 pi r squared, because the top circle and the bottom circle, plus 2 pi r times height. Because if you remember, if you take that side pan off, you slice it and open it up, it's just a big rectangle. So the length is the circumference of the circle, and the height is the width of the radius, and width of the rectangle. Okay, so that's the surface area of a cylinder. Now, notice now that we have 3 different variables here, don't we? Yeah? Okay. So it says, if the radius of a cylinder is always 1/4 the height of the cylinder, how fast does the surface area of the cylinder change with respect to its height, with respect to its radius, include proper notation? Oh, that's easy for you to say. Okay. So you can see this is a related rate question because it's talking about how fast something is changing compared to how fast something else is changing. Yes? Do you see that? Notice it doesn't say anything about making something as big as possible or something as small as possible. Yeah? See the difference? Okay. So if the radius of the cylinder is always 1/4, I don't know what that's telling me, but let's move on. How fast does the surface area of the cylinder change with respect to its height? So that means I'm looking for d surface area dh. Yes? Okay. So let's do the derivative. That would be, that first guy would be 4 pi r dr dh, yeah? Plus the second guy, that involves the product rule, doesn't it? You got 2 pi r times h. So that would be the derivative of 2 pi r is 2 pi, and then that's times h, plus 2 pi r times the derivative of h. What's the derivative of h? With respect to h. That's just 1, isn't it? Yeah. So that would be it. So is this true? Is this the derivative of the surface area with respect to height? Do you agree with that? Yeah? Okay. How about with respect to radius?
Wouldn't we need a dr over dh?
What? Oh, yes.
The product property.
Yes. Oh, my goodness. That's embarrassing. 2 pi dr dh times h. Thank you. Nice job. Good. Thank you for disagreeing with me. Okay, now let's take the derivative of the surface area with respect to radius. You ready for that? So the first one is just going to be 4 pi r. Yeah? Because they kick out a dr. Because I'm taking respect to radius now. The second one's going to be 2 pi times h, because it would be a dr there, plus 2 pi r dh dr. Yeah?
To be fair, though, you're not taking the derivative of the second. The first thing
I'm taking exactly what it says here. What does that say? Derivative of the surface area with respect to r. Right? We good? Now let's hop down to C. How fast does the surface area of a cylinder change with respect to time? Well, that's going to be dSA dt is equal to, well, that's going to be 4 pi r dr dt, right? And 2 pi dr dt h plus 2 pi r dh dt. Notice we're not really asking any questions here. We're just kind of getting practice on this implicit differentiation stuff, right? Paying attention to what with respect to. So notice this one here. If I was to answer this, if I was going to use this to answer a question, like maybe I want to know what the surface area rate of change is, I would have to know the radius at a certain point, the height at that same point, and the rate of change of the radius in order to answer that, wouldn't I? They'd have to give me all that information. Right? Notice down here, if I want to know the surface rate of change of the surface area, I'd have to know the radius at a certain point and the height at that same point, and the rate of change of height with respect to radius. If I don't have that, I can't answer it, right? You all good so far? Down here, what do I need to know? Back up here? I'm just pointing out all the variables that I don't know. If I'm trying to find this, I don't know r, I don't know h, I don't know r, I don't know dh. I'd have to know all those things. Yeah, right? And here goes there's a lot more stuff, right? I need to know r, I need to know the rate of change of radius with respect to time, I need to know h at that same time as I do r, and I need to know the rate of change of, there's a lot more information that I need to know. And if it doesn't give me that information, I can't do it, right? Does that make sense? Okay. Now, let's go back up here. It says, if the radius of the cylinder is always 1/4 the height, that gives me some information, doesn't it? So what if down here, I tried to find the rate of change of the surface area with respect to time, and all I knew was dr dt. I didn't know dh dt. You see the problem? I'd be able to do everything. I could find r, I could find h, I could find dr dt, but I couldn't find that. Am I stuck? Yeah. I can go, good. I can go back over here and use this information. And what I'm going to do is I'm going to go back to the original equation and play with that first before I take the derivative. Yeah, exactly. So if, where is it? If the radius of the center is always 1/4 of the height, that means radius equals h divided by 4, right? If I'm trying to get rid of the height, I actually want 4r equals h, yeah? So then I can go back to this original equation and say, okay, surface area is equal to 2 pi r squared plus 2 pi r times 4r. And notice my h's are gone now, right? So now I really have a 2 pi r squared plus an 8 pi r squared. Oh, look at that. I actually have a 10 pi r squared. That's nice. So now I just take the derivative of that, and I could plug in my r and plug in my dr dt, right? And we could have done the same thing if we only knew dh dt. We could have got rid of the h and put in an r. I mean, got rid of the r and put in h. Okay? So, the 3 minutes left, we're going to do this last question here. So all that prepared us to do this. So let's pretend we haven't done any of that stuff up there, and we're just starting from scratch. The surface area of a cylinder is increasing. So the fact that it said increasing, I'm thinking, oh, this might be a related rates problem, right? By 2 pi square inches per hour. And the height is decreasing. Yeah, there's another rate. This has got to be related rates, right? By 1 inches per hour when the radius is 16 inches and the height is 7 inches. How fast? Okay, here's the question. How fast is the radius of the cylinder changing? And where's the when? There's the when, and there's the question. Okay? Why do I care about the when? Because that tells me what goes in the ice box. So here's my ice box. The question is, so what is my question? What is dr dt? Right? When what? R equals 16 and height equals 7. Yeah? So that's the information in the icebox. That's the question in the icebox. So now I need to somehow, let's figure out what information I have. So the surface area of a cylinder is increasing. Ah, what's that? Surface area of a cylinder is increasing. dSA dt by 2 pi square inches per hour. We all agree that's dSA dt? Is that true all the time? It seems like it says it's just increasing like that, right? And the height is decreasing. So that would be dH dt, right? And it's decreasing, so that would be negative 0.1 inches per hour. Yeah? And I think that's all the information. So we need a formula that relates dSA dt and dH dt with dr dt, don't we? Because that's the two that I know. Now, if I had one that just related dr dt with dH dt, that would work. I just need some equation that relates this with at least one of those. If it has to be both, that's fine. I just need to be able to plug things in and get the thing I want, right? So, do any of those equations I did up there relate to the things I need? The one right above it worked, didn't it? I have to do the derivative with respect to time because that's what all my derivatives down here are, right? This is ds dt, dh dt, and dr dt. So I'm going to grab that equation, dSA dt, and that'd be 4 pi r dr dt, right? Plus 2 pi dr dt h plus 2 pi r dh dt. Okay? Now what do I do? I don't set it equals 0. That's the optimization problem, right? What do I do now? Plug in everything that I know and solve for what I don't know. So I can replace r with 16, I can replace h with 7, I can replace dh dt with negative 0.1, and I can replace dsa dt with 2 pi. Put all that stuff in, and I just do some arithmetic to find the argument. Yeah? Okay. So that is a classic related rates problem. And I think we'll end there.